Started. So in the last class, we ended up talking about a TAM pipe. A TAM pipe is generally used for something we call hydrofracturing or fracture grouting, sometimes for permeation grouting, as we'll talk about in the subsequent slides. It has a very particular application for one of the 4 or 5 types of grouting that we'll talk about later today. So, the advantages of a TAM pipe, we sort of covered this in the last lecture. You have quite a bit of control over where you want to inject it in the ground, which type of soil or geological layer you want to inject the grout into to reduce its permeability or cause an increase in stress and cause subsequent stress redistribution and move the soil as you wish. You can also reuse each port or membrane sleeve at each point to inject at several instances. Moreover, you get control over volume and pressure. So these are perhaps the advantages of using a TAM pipe. Disadvantages, it takes time to drill, replace with a TAM pipe. TAM pipe itself may cost additional, depending on whether you use steel or plastic TAM pipes. You may encounter limitation in terms of depth, as it can get costly if you keep on extending the length of these TAM pipes. There is wear and tear each time you use these TAM pipes, and they may not have too much longevity in their function. So these are the general advantages and disadvantages of using a TAM pipe. Now, moving on to the more important aspect of grouting. We talked about so far the various parameters we need to consider when designing a grout injection in the field. We talked about how the rheology of the grout is important. And why is that? Well, if your grout cannot flow very far, then perhaps it's more ideal for a particular type of grouting, such as compaction grouting, for example. You don't want it to travel far, you want it to be very viscous, you want it to have high pressure to displace soil wherever you're injecting it. Or conversely, if you want something very mobile, you want a very large influence area, then you want a rheological behavior, a model that's very low in viscosity and can travel quite easily through the voids. What we see on this slide are the 5 main types of grouting. These are commonly used in Hong Kong. At the top left here, you see penetration or intrusion grouting. This one is trying to fill in existing fissures in the ground, perhaps existing cracks. You're not trying to cause additional fractures in the ground. So you're not doing penetration grouting at particularly high pressures. You just want a relatively mobile grout design to permeate and move into any voids in the ground. Most of the time, the intrusion grouting will require very low pressure. Now, if you look at the next type of grouting, penetration or permeation, this has less to do with fissures, so more to do with soil compared to rock. If you look at penetration grouting or intrusion, this is more trying to fill in cracks with rock material. With soil, we have penetration or permeation grouting, where you have more or less the same principle. You have a relatively mobile grout that has a pretty high viscosity, low viscosity, so high viscosity, and you're trying to get it to move through the voids of the ground. And that's what we call permeation grouting. The third type of grouting shown here is displacement or compaction grouting. This is where we have very slow-moving, less mobile grout injected at relatively high pressures to try to compact the soil around it. This is sort of some type of compaction as well. you're trying to increase the density or the bulk density of wherever the soil is that you want to compact. And this could be a problematic clay lens, for example. So you can target that particular depth. On the right side, the far right, we have something called jet grouting. If you recall from the earlier slides of this lecture, we mentioned that this is perhaps a hybrid approach between grouting and deep cement mixing. This approach perhaps is the most uniform in terms of the stabilized soil quality. What we mean by that is, in jet grouting, there are three approaches. There's a single nozzle, dual nozzle, triple nozzle approach. Single nozzle will inject grout at high pressure, and this rod here will continuously spin. So it's concurrently mixing the soil in situ and injecting grout. So that's for the single jet or single nozzle. For the double jet or double nozzle, you will inject grout and high pressure air. High pressure air will further increase the mixing. The triple jet or triple nozzle will have a third nozzle that injects water. The combination of the water and the air will help to uplift particles to further enhance mixing. Now, you might be thinking, when do we use single jet, double jet, or triple jet? Well, there's trade-offs. If you add air and water as you're creating jet grout columns, you're reducing the strength of your columns. You'll see later on that if you use single jet grout mixing or single nozzle jet grout mixing, you'll get the highest strength columns. However, your influence radius of your columns decrease. You can't get very large columns, but they are very strong. If you use a dual or triple nozzle jet grout mixing, you can get a much larger area, a much larger radius for the jet grout columns, but the strength will suffer. The last type of method of grout injection is at the bottom of the slide. It's called soil fracture grouting. Now, this type of grouting is quite unique in that you're purposely trying to inject the grout at very high pressures. You're not leveraging the in situ permeability of the soil, or you're not trying to move the grout through the voids of the in situ soil. Rather, you're injecting such high pressure grout that you're causing cracks. You're creating new cracks, new fissures, new fractures in the ground. And when you create these cracks and fissures, the grout will follow these planes of discontinuities and fractures and fill them up. So if you look at the bottom of the slide here, we have an example of how soil fracture grouting would work. You see, in essence, a series or networks of grouted veins in the ground. Soil fracture grouting is good for compensation. If you are carrying tunneling works underneath a particular sensitive infrastructure, such as a tunnel, you can compensate stress release by simultaneously or carrying out soil fracture grouting underneath the tunnel to protect it beforehand. We'll talk about some of these applications later on. So these 5 approaches that we've shown are just methods of injecting the grout in the ground. You still have to consider the grout composition based on the in situ soil properties first, and then you decide what type of injection method you want to inject. And as we mentioned at the top, the consistency in soil type, injection pressure have to be considered beforehand. To select the right injection method, you have to consider the application. Now, on the bullet points here, there are some applications. If we want to just fill a very large, perhaps karstic void or cave in the ground, we can just fill it with cement grouting. There's nothing complicated about that. You just put a pipe in and you fill up this cavity. So the second type at the bottom is permeation grouting. If you want to reduce the permeability of the ground, for example, for hydraulic cutoff, then you can use permeation grouting in soil. The third type, on the third bullet point, is if you want to compensate and you're expecting ground movements from tunneling, excavation, and you want to minimize the damage to adjacent infrastructure, then you'll carry out compensation or fracture grouting. The third type here is if you just want to compact the soil, then you can inject high pressure, low mobility bulbs and carry out compaction grouting. So it really depends on what your prevailing objective is in the field. There's another term here, compensation grouting. The most common form of compensation grouting is by using fracture grouting to do it. But you may ask, can we use other types of grouting to compensate stress release and ground movement? Well, yes, you can. But more often than not, we use fracture grouting to do it, as you'll see later on in examples. At the bottom of the slide here, we should see a more representative picture of what jet grouting is like. When you carry out jet grouting, you're mixing, here we have two nozzles, you have probably grout and air. You're lowering some sort of rotating core in the ground, and you're forming columns in the ground. These columns can be used to form a retaining wall. They can be used as perhaps a cutoff for hydraulic flow. They can be used as a barrier to contain hazardous waste. So jet grouting can be used in an array to form as a barrier, or you can use it as some sort of improvement in bearing capacity. For example, if you put a cluster of these jet grout columns together, you can perhaps increase the bearing capacity of a shallow footing. And we've mentioned already that jet grouting is a special hybrid type of chemical improvement, somewhere between grouting and deep mixing. And the triple, single, dual jet is basically just depending on what type of additional fluid you inject on top of grout, whether it be high pressure air or high pressure water. The air and water help to erode the in situ soil, so you can replace it with more grout material. High pressure air and water can also be used to flush out some material and lift it as well. So this is providing you with a bit more details of the different injection methods. More importantly, what type of soil is beneficial, or the right type of soil to use for each type of grouting? Well, this table here helps us to understand that. If you have very coarse-grained cohesionless soil, such as gravels, sands, then you can take advantage of, at the bottom here, it shows the main range. So if it's a solid line, this is the most common use of this type of grouting. If it's a dashed line, you're basically stretching the extent or the limits of this type of grouting. Now, for coarse-grained soils, as we mentioned, permeation grouting is the best, because anytime you're trying to permeate, if you have a very high permeability, then the grout moves around quite easily and you can get a large improvement area. Compaction grouting, if you have a very low mobility grout, is also good for pushing aside sand and gravel to compact it. It's not so helpful, however, compaction grouting and permeation grouting for clay and silt, fine-grained soils, or sometimes we call them cohesionless soils. Permeation grouting, for obvious reasons, for clay, if you have a very low permeability, anything less than 10 to the minus 9 meters per second, you'll find it very hard pressed to get the grout to move between the voids. Soil fracture grouting is, as you remember, the approach where we create our own fissures in the ground. We purposely inject high pressure grout to form cracks. Now, based on this principle, you can apply this method to clays and silt as well. Even though they have low permeability, we can still leverage very high pressure to form cracks in the ground and have the grout move preferentially through these cracks. So we don't have to care too much about low permeability or fine-grained clays and silts. Likewise, if you inject grout at high enough pressure and you have enough overburden pressure, that's a typical rule of thumb, maybe 70 kPa or maybe 3 meters of overburden, then you can also use soil fracture for sand and gravel type soil as well. We won't talk about deep mixing yet, but there are two main types of deep mixing that we'll describe later. One is dry and the other is wet. And if you remember what I mentioned, dry just means you're mixing dry powdered binder, such as cement, fly ash slag, into the in situ soil. So if you do dry mixing, the in situ soil must have a very high water content. So it's not uncommon in marine environments or offshore projects in Hong Kong to have marine deposits with almost 100% water content. So that's more than enough water for you to leverage, and you can just put in dry binder. There's also wet soil mixing where you inject binder mixed with water of a fixed content beforehand into the ground. Wet soil mixing is more difficult to control the water content for very wet clays. If the soil is very wet and you inject more wet slurry in, you might find it difficult to control the water content, and we know by now that the water content controls the strength of our final mixed columns. And we'll talk about dry and wet soil mixing later. The type of grouting that we mentioned last was jet grouting. Jet grouting is quite versatile for a wide range of soil types. The reason is we use high pressure air, water, and grout to basically erode the in situ soil to form columns and to mix it. Now, if the pressure of your jets is high enough, you'll be able to erode and wash out sand, silt, and clay without a lot of problem. However, there are limitations with jet grouting. You probably won't use it for gravel. Gravel has a very high friction angle, can be up to 40 degrees, right? So then it's very high strength, and you'll find it very difficult to erode in situ gravel to form a void to create a monolithic grout column. It'd be very non-uniform if you tried to do it in gravity. So what we see here is, in essence, a range of applications for idealized conditions. Bear in mind that we're talking about homogeneous soils here that are quite uniform. In the real world, you have very complex geology, you have layers of perhaps sand, layers of clay, layers of or pockets of coarse grain material. So you would have to adjust your grouting method based on the type of soil you encounter. For example, if you're carrying out jet grouting through multi-layered soil, you would have different mixing properties for the sand layer compared to the clay layer that you'll encounter. So you have to account for these issues, and this is just a general guidance on what type of grouting method to use purely based on the particle size diameter. There are a very wide range of grouting applications that we can use grouting for. You can only see a very narrow range of activities here. If you remember the Leaning Tower Pisa video we looked at together, that in essence was some sort of compensation grouting to increase the stress levels in the ground to cause stress redistribution to try to adjust the tilt of the Leaning Tower Pisa. That was one application of grouting. As you move to the industry as geotechnical engineers, you'll find that it becomes very common to use grouting, especially if you get a chance to work on a construction site during your ski may training. You'll find that grouting happens all the time in the field, even though we have very little theory on it and it relies on experience. The top left here shows a picture of a grout curtain. So we mentioned the term grout curtain a lot. We call it a curtain because we try to install it under particular geotechnical infrastructure, so it looks like a curtain. Particularly if you look at this grout injection here, it looks like something hanging underneath this dam. So that's why we call it a curtain. It hangs underneath sheet pile wall, diaphragm wall, embankments, or dam. And as we mentioned, the objective of the grout curtain is to provide enhanced hydraulic cutoff. Hydraulic cutoff can be 100% if you can entirely prevent water from moving from high total head here to an area of low total head. Or you can just reduce the permeability here to slow down the flow of water. That's fine as well if you're not going for 100% hydraulic cutoff. Conversely, what you can do is not have any cutoff, but just increase the hydraulic path. If we can increase the hydraulic path, then we can control the seepage moving from high total head to lower total head. So grout curtains are commonly used in Hong Kong. In fact, sometimes we install more than one grout curtain. If one grout curtain doesn't work, we try to alter the hydraulic path of the water using perhaps several grout curtains, or even in some circumstances we have 2 sets of sheet pile walls. So that's one very common application of grout use in Hong Kong. Anytime you have cofferdam right beside the sea and you need to excavate inside the cofferdam, we often leverage grout curtains. This middle application at the top here is very similar to what we talked about for the Leaning Tower of Pisa. By injecting high pressure grout in the ground, you can increase stress, cause stress redistribution in the soil, and you can correct tilt. We can correct tilt for various types of geotechnical infrastructure. It doesn't necessarily just have to be underneath the building, underneath the footing, or underneath the pile. Sometimes if a diaphragm wall is moving too rapidly inwards in a construction site, you could also try to grout in front of the retaining wall, the passive side, to stiffen the soil and increase the pressure to stop the retaining wall from moving in. So it's not uncommon to use grouting to try to minimize movements of earth structures. So that's one method of grouting. And we also use grouting for underpinning, if you remember. So let's say this was a pier or a pile for a pedestrian bridge, and we want to create a tunnel underneath this foundation. We can shield the ground underneath by increasing its stiffness by injecting a lot of grout beforehand, before we carry out tunneling underneath. So this would be an example of underpinning foundation. For slope applications and retaining wall applications, we commonly inject grout for ground anchors and soil nails. The difference is, of course, for anchors, we only grout tip here, right? And they take much higher stresses, ground anchors. The ones behind the Wong Ak Keng building, those are ground anchors. Those are not soil nails, the big ones, right? Those ones we have to monitor once a year and make sure the pre-stress levels are correct. So that's why you see maintenance workers there once a year to make sure that the pre-stresses on each ground anchor is sufficient. Those are examples of ground anchors, and ground anchors are grouted at the tip to provide additional pull-up resistance in the ground. Soil nails look very simple as well, but they differ from ground anchors in that you have fully grouted tendon, steel tendon. We don't carry as much stress per soil nail, for example. You rely on the composite bulk effect of a lot of nails in the ground to stabilize a slope, for example. Soil nails are mainly used for slopes. Ground anchors are more commonly used to stabilize. Let's say there's a retaining wall here, we're trying to pull it up as we excavate. So sometimes if you're looking at your FYP or your capstone project, if you don't want to put ELS in, you can put anchors in behind the wall as well. Maybe that will save you some trouble as you're excavating. So that's one option for you for your capstone project, ground anchors. The functionality for ground anchors and soil nails are the same. You can imagine that soil behaves like a carpet, and we're just putting in a bunch of chopsticks in the ground to nail this carpet to a monolithic in situ mass of soil to prevent it from sliding. And soil nails and anchors rely on tension, mobilizing tension. This rough interface between the grout and the soil will enable you to enhance the pull-up resistance and the friction between the grout-soil interface. So that's how ground anchors work. And as you'll see in the slope class, we use grouting for soil nails as well. Moving downwards, we have the use of grouting to shield tunnel advancement. In this case, the tunnel could be advancing in either soil or rock. If it's rock with very competent rock material with very thick cover over top, you probably don't need to do any grouting. If it's in soft soil, tunneling in soft soil, then you probably need to do this kind of shielding beforehand, so you don't have a collapse of the tunneling phase. The collapse of the tunneling phase can be catastrophic for your tunnel advancing machine, your boring machine. It can also affect the safety, and if you grout enough, you might be able to affect the permeability of the ground. Let's say there is an infiltration of water into the tunnel. That could be something we're afraid of during tunneling. These are all hazards that we try to mitigate. In this case here, I guess this could almost be a plan view of the tunnel. We're looking on over top, and we can inject grouting in straight up fan like this to stiffen all the soil above. So as we push the boring machine through, we're not worried about collapse of the soil into the tunnel, because that can waste a lot of time and be very destructive. By grouting from the tunnel head, we can also minimize ground movements. Anytime you're tunneling underneath infrastructure, you can expect ground movements and settlement on top. But if we can stiffen the ground before we tunnel or advance the tunnel, then we can minimize disturbance to infrastructure. So that's a very delicate use of grouting in the field. Another one here is in the middle is we can also use grouting for excavation. Let's say you don't want to put a retaining wall in, you don't want to put a sheet pile wall in, you could perhaps leverage jet grouting. So you can use an array, almost like soldier piles, an array of jet grout columns, very spaced, very close together, and it can form a wall. So it can provide a temporary retaining structure for you to rapidly carry out whatever earthworks you need to inside your excavation. And like I said, if you use grouting to create a retaining device, you can also use it as some sort of barrier to contain geohazardous waste, perhaps radioactive waste. There's enough reduction in permeability as well. So grouting can also be used as barriers and stabilization as earth retaining structures. The last application here is perhaps relevant for the scheduled areas in Hong Kong. In Hong Kong, we're perhaps worried about karstic geology in some designated areas where there's marble, and then there's the erosion of this marble, and there may be voids in the ground. So to overcome these voids, what we normally do in practice is we can rely on geophysical means. What I mean by that is you can scan the ground, and if you read the reflection waves, you can perhaps detect some large voids in the ground. And you find out whether these voids coincide with the toe of your bore piles. If they do, what you can do is just carry out infill or filling of these karstic caves with grout, and then you don't have to worry about the giant void being there. So that's another common application of grouting in Hong Kong. And as you do your Scheme A training as a geotech engineer, you'll realize that we basically use grout for everything. You have perhaps some water coming into your site through a sheet pile wall, you might grout it. If you have a drill hole that you don't use anymore, or you have a monitoring well that you don't use anymore, you'll just fill it with grout. So grout comes in handy all the time in geotechnical works. So I want to cycle through the different types of grout injection in a bit more detail here. So let's take a look at permeation grouting in soil and rock. So I'll play this video from Remco. So this is a device that would carry out permeation grouting. You drill your borehole, or not borehole, you drill a hole in the ground, and then at the tip of this device there's a packer. So you can basically, if you look here, it's a packer, this black thing that expands and doesn't let the grout travel to other regions. So if you want to grout all these fissures in the rock, you fix the packer there and you just let the grout go until you're not getting any more feedback from the ground. Likewise for the soil here, you can inflate the packer, fill it in until refusal. Now what's interesting is if you look at this video, you keep on injecting drill holes in the ground and you can form some sort of almost like a beam of grout in the ground to increase the bearing capacity. So it's like an in situ grout beam in the ground to strengthen your soil. So this is an example of how you can use grout in a structural form to strengthen the soil. So I'll show you this video again. So focus on the drilling, and the black tip here is a packer. So you bring this up, inflate the packer, and then the tip will have high pressure grout to infill. And then we bring the packer up to interface between the soil and the rock, and then we basically let the grout go until refusal. We bring the packer up to ground surface, pack it, and let the grout go until refusal again. And where you see the change in color in the soil, this is the permeation process. This is where the grout's moving through the voids, and this would be a repetitive process if you're looking for composite improvement, or if you just want to locally reduce the permeability or improve the ground. You can just have one drill hole. Major applications of permeation grouting. We can use it for underpinning. And if you look at this permeation beam here, you can perhaps understand what I mean by underpinning. Let's say you have some foundations on top, then you have this nice grout beam in the ground that can minimize ground movements, right? So that's an example of underpinning existing foundations. The rocks and fissure in the video, that animation that I showed you, is an example of sealing cracks, joints, and other discontinuities in the ground to improve the permeability situation in the ground. If you can form a nice composite beam like this, you can also use it for excavation, tunnel shielding as well. Permeation grouting in sand and coarse grained soils is also good for reducing permeability and minimizing hydraulic flow, or using it as a cutoff in essence. And with the cutoff, of course, you can reduce permeability below embankments and dams. And through this permeation example of the soil, I'm sure you understand how bearing capacity stiffing ground can improve. You can also, I received a question from a student today about, I think this is one of their interview questions. What are some problems? Name one problem related to post land reclamation in Hong Kong. But the answer must be residual settlement, right? Like secondary consolidation creep. We still have to calculate that after ground settlement. The second part of the question was, I think if you have settlement, how to deal with existing pipes in the ground. Well, one way is just you monitor the pipes, right? This is a passive approach, you do nothing. You put settlement markers on the joints of a pipe. So the pipes fit together like this, right? If you put a settlement marker on the joint, you can monitor it with time. And then if you have, let's say, 3 markers here, you can calculate how much distortion your pipe has experienced. And we know when, at what angle a pipe will pop out. So you can monitor using a passive approach, or an active approach. You can carry out permeation grouting underneath to provide a very stiff platform for your pipe. So this is one example of what you can use. But this is interesting that they would ask you that during an interview, because it's such a practical question. Anyhow, yeah, so you can use it for example G here on the slide. Last but not least, we can reduce permeation and permeability in the ground. And at the bottom of the slide here, we talk about what's the typical strength. You can get substantial strength here. We're talking about megapascals, right? We're not talking about kilopascals, we're talking about megapascals in unconfined compressive strength. So there's substantial strength improvement if you want for permeation grouting. And typically you can reduce the permeability in coarse grained soils all the way to 10 to the minus 7. So this is the boundary between silt and clay. So you may not be able to achieve 100% cutoff, but you can substantially alter the hydraulic path of the soil. So we can also look at the use of permeation grouting using a TAM pipe. So let's take a look at this animation. So again, we have a special drilling device, incline drilling here. We drill, insert the TAM pipe, and then we use this handy grout machine here on the left of the slide. And you can see how the TAM pipe has the sleeves here, so you can carry out controlled bulb injection. The reason that they can overlay the bulbs, this permeation grouting, is because, well, I guess the grout hasn't set yet, right? If it's set, then it becomes a hard bulb and you might find it difficult, right? So, moreover, what they do afterwards is they can use the grout to do two things. Notice that the grout is underpinning footing. If you don't underpin footing and you carry out excavation, what's going to happen? Well, then your building will move into your excavation, right? And interestingly, this grout can also be trimmed off, excavated to be used as a retaining wall. So these are some uses of grout in the field. Let's take a look at the video again. So we drill our inclined drill hole just through the beside the shallow footing, because we know we want to excavate beside it, and we're worried about stress release and the movement of this building into the excavation. Then we inject grout using permeation grouting to slowly move through the voids of the soil, and we can use TAM grouting to have a very uniform effect at spaced depths. And again, two purposes here. Number one, underpinning the footing. Number two, you have a nice retaining device to use. As long as the depth of the wall is not too substantial, it should be okay. So this is another example of permeation grouting with the TAM pipe in this case. So if you remember the TAM pipe, it has the sleeves in it, and we can target the elevations that we want. Now in this case, I mentioned soil fracture grouting is quite useful for compensating the ground. When we talk about compensating, often we're talking about compensating ground movements. So in this video, before I play it, you can see that this existing building that's founded on a shallow footing is already tilted towards the left of the slide. And I guess what's going to happen is this animation is going to show soil fracture grouting take place to try to correct the tilt. So bravely enough, they excavate first. And then they put horizontally drilled TAM pipe again. That's brave to excavate first. Okay, and then now we create these veins in the ground, right? These networks of veins. So it's very high pressure grouting, and we're causing cracks. And these cracks will help to create additional stress in the ground to prop up the soil. Now, this sounds really easy, right? It's not easy. It's very difficult to carry out soil fracture grouting. And to the point where you can create tilt back to perfect horizontal elevation, this is quite theoretical. I guess it's quite difficult to carry out soil fracture grouting to that kind of accuracy. But the point that soil fracture grouting is good for compensation is because it's not like one massive ball of grout that's uncontrolled, right? You can slowly form cracks and fissures, and the combination of these veins in the ground can slowly increase the stress in the ground, rather than one big injection displacement of the ground with a very dense piece of grout. that might cause overcompensation and cause the building to tilt the other way, for example, right? So you want to slowly inject with these veins, right, and see what happens, take a monitoring approach, and then you move on, inject more veins in the ground at high pressure to see if the increased stress can correct the tilt in the ground. So this is soil fracture growth taking place. And you can imagine this is just for footing. Sometimes when we're tunneling, we create settlement troughs, and we might want to carry out soil fracture grouting to create a protective beam or shield on top. And we use soil fracture grouting because it's not as dynamic. It's a slow fissuring process, so you don't have to worry about sudden heaves in the ground. So that's the advantage of soil fracture grouting. Now, not so easy to do in practice now. You have to be very familiar with how to form fractures in the ground. Of course, there are theoretical considerations, right? But I think that's well beyond the scope of this class. And in fact, all types of grouting we talked about, fracture grouting, jet grouting, displacement, compaction grouting, there's actually analytical equations to do this, but I think this is well beyond the scope of the class. However, for example, if you're talking about permeation grouting, why do we talk about rheology? Because you need to use some concepts from rheology. What's the shear rate, what's the viscosity, so we know how far it permeates. So there can be calculations done for each type of grouting, but for the purposes of this course, you just need to know the type of grouting. And it's not so common that you would carry out a grouting design as a geotechnical engineer unless you were a specialist in grouting. And if you work on site, you're probably the one commissioning the grouting. You're asking the grouting contractor to do something for you. And they often can also design the grouting works as well. So this is soil fracture grouting. And if you want to look at how the veins look like, an interesting picture here from Hayward Baker is here in the ground. So after soil fracture grouting was carried out, they excavated the ground, and you can see these black parts here. These are the fractures formed from the high pressure ground, and I guess the other stuff is the soil, and you can see that how it looks like a network of veins. Likewise, we can use TAM sleeves for fracture grouting. We can inject the grout where the rubber sleeves are so that we can have some control over the location of the high pressure injection. TAM pipes are quite versatile for injection location, as you'll see throughout this lecture. Now, soil fracture grouting requires high mobility grout at high pressures. The high pressure is to form the crack, and the high mobility is to ensure that the grout is not too viscous, so it can travel quite far through these fissures that we form from the high pressure. We can inject through the same TAM sleeve again and again, cause cracks, and create a network of veins until we compensate enough of the ground that we're interested in. So this is soil fracture grouting. Now, I talked about other applications of soil fracture grouting. If we look at the bottom of the slide here, now, one challenge with grout injection is you have to ask yourself, do you have good drill holes beforehand? We always say that you don't need a lot of good equipment or fancy big rigs to inject grouting, but you need a very systematic networks of drill holes. Now, if you look at the bottom left figure here, you have to have in situ drill holes. Now, if you want to do horizontal grouting, so right here, what happens is this is sort of like a grout beam that I talked about. So we keep on injecting grout in the ground until we form some sort of composite soil beam. What's the purpose of the soil beam? Well, you have a building on top here, and before we carry out the tunneling work underneath, we put a grout beam here so that it stiffens the ground substantially here. And then when we carry out tunneling, the stress release will redistribute so that it doesn't cause substantial settlement of this building here with a very shallow foundation. Now, to create this soil frac beam, we have to have access to this particular depth in the ground. Some ways to do that is you can create a shaft, excavate a shaft, and then you can put a drilling rig and carry out horizontal drilling to the location underneath the building. If there are existing service tunnels that you can use, it can be for other utilities, for example, then you can leverage these service tunnels, put the rig in, also carry out horizontal drilling, and then you have these two drill holes to insert the grout. Likewise, you can create an excavation here so you can get to a lower elevation and go horizontally, right? Why do we want to go horizontally? Because if you go vertically, you can only create a column of grout. But if you go horizontally and have a TAM pipe, then you can create a beam of grout. So we often take advantage of these beams of grout. And you can also do this from the surface, right? But you'll find it difficult to get this beam done with one single drill hole here. So this schematic from Hayward Baker is just showing you that and to carry out soil fracture grouting, you need significant access to where you want to grout. There's another use of it here. If a client allows, you can also go inside their basement, put the rig there, drill right through the basement, and carry out the grouting works like that. So that's how this soil frac beam would work. Now, if we look at the right side of the slide here, here's another example of soil frac being used to shield a pier or a column or a pile, for example. Probably not a pile because it's so shallow, but maybe a bridge pier on a shallow footing. So there's a nice applied load here with 970 kilonewtons, and we know that we will be tunneling underneath. So before we carry out any tunneling, we can construct a shaft here. We can then use the shaft to create a grout beam to minimize any settlement cost when we do tunnel underneath this perhaps bridge pier here later on. And often when we carry out these soil fracking operations, we have a very heavily instrumented site. By that, you can see we can have inclinometers in the ground, we can have extensometers to capture the settlement inside the ground, you can monitor groundwater changes, so make sure your grout is not significantly affecting the hydrogeology of the ground. Earth pressure cells to make sure you're not blowing out the foundation. If you inject the grout at too high pressure, you can cause cracks in these concrete slabs as well. So these are the details that we need to consider when we carry out soil fracture grouting. And soil fracture grouting is again nice because we don't have to inject very high volumes all at once. We form little network of veins to inject very small volumes, see the response of the ground, and then create more networks of veins rather than bulbs of grout all at once. Now I want to show you another type of grouting. This one here is called compaction grouting. Compaction grouting, as you can probably see, is less friendly in terms of controlling displacement. So this house here is sitting on, I guess, a fault here. Looks like a fault. So again, you would drill a hole in the ground. You would get to your target depth. And then let's say the soil is very loose here because it's a fault. It means that it's undergone a lot of shearing, right? So the soil is very loose. And then you can inject grout into the ground. So it's coming up from the bottom if you look very carefully. So we're basically densifying this very loose soil, which is often found in faults or previous failures. You can treat this as a previous shear failure in the ground. And the soil's been sheared, it's quite loose. And we just keep on injecting the ground until we fill up this entire fissure in the ground. And then we're not worried about this house falling in. You can see there's already a service crack here on this building. And we just keep on creating bulbs to compact the soil. That's why we call it compaction grouting. You can also argue that this is a method of deep compaction. And then the cracks in the house mysteriously disappear. So it's Yeah, that's one example of how we use compaction grouting. I don't think it ends there, right? They do more things. No, that's it. They fix the house. So what you saw in the animation here, I'm out of time, so we'll carry on to the next class again. All right, thank you. I saw some emails, questions. I will answer them. I just need to get around to them.